We welcome you all to the session 3 of 4 days 4. I welcome Professor Dattatray Sawant once again for the session 3, and the topic for the session will be NI LabVIEW for CROME application. Over to you, sir.
Okay, so very good afternoon, everyone. I know that this is a difficult session because after lunch, but fine. Still, I will show you some of the interesting equipments which we have at Mukesh Patel. We usually do training for the students and industry persons. So here, the kit which you can see in the camera, that is called mechatronic sensor kit, where there are different types of sensors are available, starting with piezo, encoder, reflective optical, magnetic field, the pressure, infrared. There are also potentiometer, switches, thermistor, the strain gauge, sonar, and this is developed by third party called Concert. So this is the specifically educational kit where the students can develop different application with respect to the sensors and instrumentation, and they can develop the good mechatronics application. So this is, I will say, this is called prototyping board. This is prototyping board. What is this prototyping board? That I would like to answer by showing other instrument. This is called NI LabVIEW 2 board. We have a number of pairs for all these devices. So at a time, almost 10 students can perform the practicals on different devices. So this is, we have NI LabVIEW second version. Also, we have the NI LabVIEW 2 plus version. So what is this and why I did this is called prototyping board. Ma'am, am I audible now? Hello, ma'am.
Yes, sir, you're perfectly
audible. Thank you. So if you observe, this is the workbench, and this is specifically used for the academia. We use this facility during pandemic as well. The reason behind this, if you observe this side, the oscilloscope pins are available, the function generator pins are available, digital multimeter. Also, there is breadboard. So with respect to this NI LabVIEW series prototyping board, you can perform digital electronics practical, BW practicals, some of the analog electronics practical, also linear integrated circuit practical as well. Okay, because you don't require the specific, the bulky oscilloscope, function generator, and the power supply. With the help of this board, you can efficiently perform all the practicals, and which gives the real effect. So why this is called prototyping board? Because this is like video game. So this is the main workbench. This is the prototyping board. So on this, I think just now mentioned, we can perform the practicals on digital electronics, analog electronics, linear integrated circuit, also BW practicals, and with the same prototyping board, you can put in this NI LabVIEW 2 and you can do this prototyping. You can integrate this way, and student can use different sensors. They can also do calibration initially, and they can actually take the real-time readings from this prototyping board, and they can utilize for their specific application. So this is LabVIEW NI LabVIEW 2 board, and this prototyping mechatronics prototyping board is developed by the third party called Concert. So we have this. I just show other devices. During my presentation, if I'm not wrong, that time I showed some of the hardware examples, starting with the Wi-Fi based DAC card, the USB based DAC card, and this is also one of the advanced DAC card. This is USB 6341 series. This is also USB 1, but this is the not micro USB DAC card. And but just now I mentioned micro USB. So every specification of the DAC card is varying with respect to the AI and DIDO configuration. So this NI USB 6341 series, or we can say USB X series, having 16 AI and 2 AO and 24 DIDO. So this is the configuration. So with the help of student can develop the data acquisition application uh, uh, and which you can integrate to the LabVIEW. I sincerely apologize because due to this virtual mode, I cannot make the integration and I can show you, but still I'm showing the probable hardware devices, so which you can integrate to the LabVIEW, and we can develop the industry standard application. That is the specialty of the LabVIEW software. Just last, this is the second device, the DAT. I just showed the MyDio, which is the MyDio controller. So this is we have integrated this MyDio to one bot, but that is fine. So this is the MyDio controller, again developed by the National Instrument, where the control is just I mentioned during my presentation, which is FPGA based. Many of the faculty probably their domain is embedded. So you know that usually student like two processor only, the Arduino and Raspberry Pi. I will say indirectly they will like more Arduino because the codes are very easily available on the net. But they don't prefer the advanced controller like PIC, microchip, DSP processor, MSP430 controllers, and this is a FPGA based controller. Because why they don't prefer? Because with respect to the programming, because that is advanced programming knowledge they require. So the specialty of this MyDio controller, where also you can do the real-time data logging and you can control any application which is embedded based, robotics based, mechatronics based, and the control based. I just would like to highlight the cost of this board. Specifically, if you go for the Arduino, it is hardly 1,000 or up to 3,000 up to mega version. But the cost of this board of MyDio is around in INR is 60,000 rupees around. So which is very costlier, but very much efficient, very much faster as per the application. Okay, that's all. I just want to introduce all these devices which we have. So when we have the physical FDP, we usually train our industry person with these devices. So I just continue. Just share my slide first. So now we will be developing some of the control applications where as the term control, so what obvious the first there's a modeling comes in a mind. Also there are differential equations. So we'll understand how to solve that, and also as I committed at the start of my session, we'll also try to integrate the math strip with the LabVIEW. So how can we do that? I hope my screen is visible.
Yes, sir, we can see.
PPT is visible?
Yes, sir. Yes, yeah. Sir, PPT is visible.
Thank you. So the first, the CROME application, the meaning of CROME is the control, C for control, RO for robotics, M for mechatronics, and E for embedded. So just now I shown different devices. We have the mechatronics sensor kit, we have the DAC, we have also the NI-based prototyping board, and we have also the MyView. So all these applications we can cover when you integrate all these devices. Some of the devices are manufactured by NI and some of the devices are the third-party devices. But yes, I strongly say we can integrate the third-party devices also with LabVIEW, because we have the Boss Rexroth setup at Kish Patel. So we have integrated our PLC, which is third-party, to the LabVIEW. Also, we can integrate Raspberry Pi, Arduino. The KUKA is one of the STEM robotics company. in the market. So we have also integrated KUKA robots with the LabVIEW. But to do all these things, we require in earlier session we studied the basic. Now we'll go for the advanced. I do understand due to the student version constraint, probably some of the blocks will probably not available at your end. But these are the recorded session. You can refer afterwards when you get the professional version of LabVIEW, and you can use that. So when we look over these are the two typical system. One is aerator and one is the water tank. And these are the typical the differential equations. I won't go in those differential equation because that is a different aspect. But this is also one of the system. Yes, so we'll understand this basic dynamic system. So dynamic system is represented by differential equation, and when we talk about differential equation, very simple, or we say called modern control theory. Now, the difference, the classical and the modern, very simple. When initial conditions are zero, that time we use the classical control approach, the transfer function approach. But when initial conditions are non-zero, when we have to consider the initial condition, that time we'll use the modern control approach. So this is simple. I believe the SSM model, state space model, x dot equal to minus ax plus bu. So this I am doing very simple one, not the advanced control system. Very simple equation. The x dot, which is dx by dt, equal to minus ax plus bu. So if I would like to draw the block diagram, so what is x? X is the state space variable. U is the input. B, A, B are different matrix. A usually called system matrix. B is called as input matrix. So with respect to this mathematical equation, sorry, we are developing the block diagram. So if you observe here, so U is input, which is multiply B. So that's why there is a multiplication. Then x dot, but we require x. So x dot, when you integrate, we get x. And which is minus, so there is a negative feedback with multiplier of a here, and again we get this complete, and finally we get the our output, okay, which is x dot. So x dot equal to minus x plus b. So this way we can develop the block diagram. Once we develop the block diagram from the differential equation, we can easily implement because we know the components. We know the components. U is the input, the x is a state space variable. We require one integrator model. We require gains. So we can say here A and B are gains. So these are some of the examples. That is fine. I won't waste because I usually do for the students' perspective. But I know you are all are faculty, so I won't waste time on this, giving these exercises. So this is famous simple spring mass damper system, and that is also one higher order differential equation, second order higher order differential equation. M x dot x double dot equal to f minus dx dot minus kx, where x is the position, x dot is the speed, x double dot is the acceleration, f is the force, which is the input, which is the control signal, and d and k are constant. So same way, in SSM model fundamentals, mx dot equal to f minus dx dot minus kx. So if we take the m on the other side, so it will be x double dot equal to f 1 by m f minus 1 by m dx dot minus k by m x. So as I mentioned during my start of the session, you can integrate the MATLAB with the LabVIEW. You can integrate different softwares with the LabVIEW, not only the MATLAB, but different softwares. Just you should know the basic, how you can integrate the different third-party hardwares and software to integrate with LabVIEW. So there's a Modelica, there's also ANSYS, there's a SolidWorks as a mechanical aspect. So all these softwares you can integrate with LabVIEW. Also, third-party devices like Raspberry Pi, the PIC controller, Arduino controller, some of the robotics software, KUKA robotics hardware and softwares, Yaskawa Motoman bot also we have connected with this lab. So this is a simulation loop which we require in control and simulation model. So this is simulation loop is similar to the while loop, but which is available specifically in the control and simulation model. So this simulation blocks, again, there are different categories like continuous system, discrete system, nonlinear system, and so on. So today we are developing this x dot equal to minus ax plus bu here. So I just open the LabVIEW screen. So if you observe here, I'm just sharing the screen. Give me 1 minute. I hope screen is visible.
Yes, sir.
Okay. I just share that block diagram in the chart. So probably, okay. So I have shared that image also with you. Okay. So we'll develop here. So as I mentioned, in control and simulation model, probably at student version, only these two blocks are available, if I'm not wrong, which I also confirmed in earlier session. Anyone is having these all 5 blocks in the participant side? I request participant to check. Can you please reply on the chart so that I can understand that whether you have these modulars or not? In control, right click on the function, there's a control and simulation module. Just check all these models, sub-models are available or not. PID, fuzzy logic, simulation, control design, and system identification.
So for me, all models I'm not able to see.
Yeah, that's why I'm asking, because if I get the feedback, then only I can talk, because, okay. So that is a limitation. So basically here, okay, fine. So what I will do, I will just do this, perform this program here with the help of this. When you get a professional version, because this is a limitation of student version, when you get a professional version, that time you can utilize that. So in simulation, I mentioned you have to take the control and simulation loop, which works as a while loop only in control and simulation model. Then we'll be doing what? X dot equal to minus ax plus bu. So I have shared already that image. So same in control and simulation model. You get the different signal arithmetic, like we get the gain, we require gain. We require summation. We require multiplication. So this is a summation, there's a gain block, and also we require integrator, if I'm not wrong, because I explain you from differential equation, we have to first get the block diagram, and from that block diagram, we can easily simulate the, we can develop the LabVIEW front panel and the block diagram. So we require also integrator. So in again control and simulation, just give me 1 minute. Yes. It's in simulation. Then signal generation, that is fine. Signal. We require integrator in continuous time system. So we get the integrator. Now we have to connect them. So summation is equal to, if you observe this, I will connect to this. Then there is a multiplication. You can reverse the terminals. So from here, it will be coming with a feedback. And at one term, you will be doing the constant, creating the constant. Or you can create, instead of constant, you can create better control. That is better. So this is the, if you observe on the front panel, this is my A term, which is given to the equal to, so this is minus AX. So this is given to minus, right? So this is AX, this is AX, this is A, and this is X, and this is X dot. So there is that one more gain block we require here. So there are two options. Either you can use directly the gain block, or you can use the same concept of the multiplying. So what I will do in control and simulation, in a simulation, I will go to the signal arithmetic. I will take one more multiplication here. Okay. So this I will connect. So this is I have to make BU. In U is a control signal and the BU is a multiplier. So again, I will take here numeric control, which is one is U. There's a one more control I will take here, which is B. I've seen many times that we require other type of feedback and the combination. And I did one training session at the Indore, and that time one of the participants called me for this summation term. He said we require different combination in his PhD project. So I just would like to highlight here the participant how to change the feedback and the other configuration of the symbol. You just double click on this. When you double click on this, you can vary the input. If you don't want this input, if you want to make this is plus, so these are the combinations you can make it. Okay, double click on this summation. But here for this R application, we require here plus and we require here minus. Okay. Once it is done, we require now this is all the as per the image given in the chart. This is x dot equal to minus ax plus bu. So we will take the value of a and b, and whether we just check it that whether we are able to get the step response or not on a waveform chart. So for that, in control and simulation block, again I will go to control and simulation block. There's a graph utility and there's a simulation time graph. So this is coming. Okay. And I connect this with this. So this is waveform chart. This is A and B. We have to set a value of A and B. So I have taken here 0.25. U is 1 unit step. So we try to achieve that response. Not unit step, but the step response. And the value of B is 2. There's also logic to get this value. If you want, I can just tell you how I'm getting this value. That also I share. Okay. Why I took the 0.25, 1 and 2, that also I will explain. See, if you observe the PPT, x dot equal to this is x dot. So x dot equal to minus ax plus bu. So if you observe here, if we want the response nearby step and the maximum reaching point is 8. Okay, so that value I'm getting by when I put u as a control input as a 1, the B as a 2 and A as a 0.25. So I'm actually deciding my output, the maximum output which I'm expecting, and with respect to that reverse engineering, I'm calculating the value of A and B. And that's why I set their values and just will check whether we are able to get a response or not. So if I'm not wrong, we are able to get the response. There are some settings also we have to do in control and simulation model to get the right readings. So right click on this control and simulation loop and click on the configure simulation parameters. So instead of final time 10, I will take the 20. Remaining all same. They are also called timing parameters. So fine, okay, and just I run it. But okay, here initial time is shifted. Okay. Yes. So we are getting, you can also change the appearance by doing the properties of the display format, the scales like here, you can vary from 0 on x-axis and amplitude axis is fine, is perfect. So this is the graph. So this way we can develop the VI using control and simulation module for the differential equation. I hope this is clear to everyone.
Yes, sir.
Okay. So just going further about the discrete system. So this is when we call about discrete signal, there's a fundamental of sampling time. So as per the Euler approximation, we can express x dot as a same equation in a discrete differential equation, x of k plus 1 minus x of k upon ts, and which is called x dot. So if you do the cross multiplication where ts is a sampling time, so which gives the discrete differential equation x of k plus 1 equal to 1 minus ts a into x of k plus ts b u of k. So we'll implement this with the new fundamental call, which I said earlier, the integration of math script and the formula node. So first we'll understand the formula node. What is formula node? And what is the significance of formula node? That we'll understand first. So basically formula nodes, they evaluate the mathematical formulas and expressions similar to the C on the block diagram. So we can use different built-in functions like sine, the sinc, random, max, minimum, square, root, square. So, and this formula node is very useful as per the simulation and the mathematical expression perspective. When you want to use math script in the LabVIEW, there are two ways. I will show both the ways. How can we use the math script in the LabVIEW? The one is one method is math script node and one method is math script window. So math script node create and use math script or MATLAB code with the LabVIEW. That is the significance. Or I can say also which executes the LabVIEW math script and your other text script using math script RT model engine. Okay. So that also we'll understand. So this is simple example which we are doing first using formula node. I believe with me everyone can perform this activity. The reason the formula node is available to everyone. So new VI, how to get the formula node? In structure there is a formula node. Just take formula node. Everyone please take a formula node first. Once you take the formula node on a block diagram, we'll be doing the same conversion which we did in the first session. So this is the formula also I'm giving. Now what's the difference between the earlier session and this session? If you observe in earlier session, we were using all those function blocks, division, multiplication, addition, but now we don't require those blocks. We can directly use the equation in this formula node. That's why the name is formula node. So directly I can put the formula in the formula node. So I will type TF equal to, I think this activity everyone can do because in student version formula node is available. 9 by 5 multiply by TC plus 32. So for TF and TC I require two indicators. So I will take the same indicator. I will name it as a TC. This is, name it as a TF. So one we require control, one we require indicator. From the start of my session, I'm saying that control is usually input side and indicator usually on output side. So you can change to control. So which is DC, this is TF. If you observe my earlier session, and clearly there we have used many blocks, different blocks like mentioned division blocks, addition block, and then after that we completed logic. But formula node, you have to just put the formula and you get the output. But there are some of the small things which we have to take care when we are using the formula node. The first is we require the input as a TC. So I will right click on this formula node window and I will do add input, and I have to mention the variable which I am using it, TC. You can observe there is a broken arrow, still there is a broken arrow because this is all the functions of formula node you have not used properly till now. So TC. Then we also need to create the output. The variable is TF. Still there is a broken arrow. The reason behind this, in formula node, like if you know like Scilab, MATLAB, we have to use the semicolon. So here also we have to use the semicolon fundamentals, and just as soon as I use semicolon, you can observe my run button is activated. So this is the functionality of the formula node. I just would like to also show the participant, instead of TC, if I made capital C, TC, and just will observe the impact on the program. Still it shows the error. So it is a case sensitive as well. We have to use those and correct variables only, then only formula node experiment you can perform. So we can run it, and so if you want real time, I mentioned in the morning session that for continuous mode, please use the create control, and yes, that's it. So this is the fundamental of formula node. I hope that everyone has done this activity. Kindly respond in the message or in the chat so that I can proceed further. Yes, okay. So we'll proceed further. Stop the screen. Okay. So this is called formula node. Now, just now I explained you how to simulate discrete time system mathematically. So you will do this activity, and we just observe, get the same answer what we did just now for the continuous time system or the differential equation. If I'm not wrong, using the control simulation model. So there we set the value of A is 0.25, B equal to 2, and U equal to 1. How did that set that? Because my output which I have to achieve, which is the 8. So I did reverse engineering and I calculate the value of A, B, and U. So same thing we will try to do using formula node. So this is the actual discrete model. So I agree, due to control simulation submodel you could not make it, but discrete time system at least you can simulate. So we'll perform together. So this is the equation. So I request all the participant please discrete time system using formula node. So I will take one formula node here. Just show the equation once. You want this also I will write. Yeah. So this is the discrete time differential equation will be simulating using formula node. So if you observe here very clearly, the TS is the sampling time. The A and B are the multiplier which we require, and x of k plus 1 is what you can observe very carefully, which is 1 minus A into TS into x of k. So this is the in feedback we have to use that. So what we will do to simulate this, first I will try to write this equation as it is in the formula node. Then I require A as an input, so I will create A as an input. I require B as a one of the input for to run this mathematical equation, so I am taking B. Then control signal U, but if I take U, it won't work because I have taken U of k. So I have to write here the same the name, because which is correct name you have to put it. Then I require also TS, the sampling time also. So what I will do, I will take here numeric control. The first is the stop time. Sample time, TS is a sample time. A, B, and C. Oh, but not C, this is control signal. Take the control signal. U. So I will connect this first. Okay. So this is A, B, U is connected. We require also TS as an input side. But we want to simulate it, right? We want to simulate. Earlier case, we just observe the output. Now we require the simulation here. So if you observe in MATLAB, many faculty knows the MATLAB. So there is the start time, interval time, and there's the end time. We write t equal to 0, colon 1, colon 10. So 0 is the start, 1 is the interval, and 10 is the end. So same fundamental TS, the stop time is 20, and we'll be using a sampling time here. So if I would like to make the same functionality, so I will use the for loop. I will take inside this for loop, and now connect this, connect to this, but here I have to add input as a TS as a sampling time. Then as an output side is x of k1, which we are looking. So add output x of k1. So this is x of k. How will I get x of k1? X of k from x of k plus 1. Very simple thing that there is a feedback node is available. How will you get a feedback node? In a same structure, there is a feedback node is available. This is one way to get a feedback node, or there's a one more option. You just create here input x of k, x of k1. This is x of k and this is x of k1. So when, if I connect this directly, see, you can observe, participant, you can observe very clearly this feedback node is automatically created. Just so this is one option. You can directly connect x of k1 to the x of k. Feedback node is created directly, or you can take it from structure. There is a feedback node. This option is also available. What is feedback node? Control H, which is store data from one of via execution or loop iteration to the next. So from this, it will store and even to the input variable. But this feedback also require the initializer terminal, initial condition, that is called x of 0. So I just create here create, considering here 0 only. This is also called, you can write here, this is also called x of 0. Okay. So once this is done, still there's a broken arrow because we have to show on a waveform graph. So this is, we are not doing control simulation model. I got a limitation. That's why I change my the PPTs that so that I can do some of the simulation also on the model which are available at your end. So there's a waveform chart on a control parallel. There's a graph. Then select as a graph. Chart we do inside and graph we do outside, that we have seen in the morning session. So now I will connect this. Yeah. Okay, done. So this is completed. Now I think I've shown you how to get this value of A, B, and C when we using LabVIEW. So value of A is 0.25, B is 2, and U is 1, and then we can reach to the output up to 8. This is sampling time, which I will take of 0.1, and the stop time, which I will take as a 20. So now still there's a broken arrow because the for loop should know when to stop. So this depend upon the combination of sampling and stop time. So what I will do, I will make here one function. I will take arithmetic block of division, and where I will connect t stop here, which is divided by sampling. And I will view to the the count of for loop. As soon as I connect, I think my broken arrow is removed. Now program is working very nicely. So now we'll run it and I'm getting the output. I hope this is clear to all participants. So same result we received as the previous example, which we did during the dynamic system simulation using control and simulation. When I discussed with Sujita ma'am, that was a limitation that many participants have in the student version. So I thought to make this experiment, so at least you get the same results also you can observe. Can I proceed? Student, please participate. Sorry, extremely sorry, faculty members. Please reply in a chat. Can I proceed with the next simulation? Okay. Thank you. So this is something we started with the dynamic system. We simulated discrete time system as well. I said these are the CROME applications, so I have to do programming. So now we'll see how to integrate the LabVIEW with MATLAB. So there are various ways. The first way is the tools. In the tools, there is a MathScript window. I just want to hear from the participant that in student version, this function is available. Can you just put in a chart whether this function is available in student evaluation version? On front panel tools, there's a MathScript window. Can you put in a chart so that I can get the feedback whether this MathScript window is available or not available? In tools, there's an option. Fourth option is MathScript window. Participant, can you please reply in the chart so that I can proceed further? I think. Thank you, Sanjay Patil sir. Thank you. So I just click on the MathScript window. So it takes some time. So this window get initialized. So once you get this window, you can observe this is MathScript window is available in LabVIEW. So there's a variable you can define. There's a script you can write. Okay, and you can save this as a M file. So what I will do, whatever experiment just now I did in a mathematical format, like in MATLAB and Scilab, we write a mathematical equation, we define the constants or we define the variables. We use plot command and we get the output. Okay, so I'm having already that code is written with me. So I just share that also with you as well. So this is the code, what we did just now, but that is in MathScript. Just I will put that code here. So I won't require the clear. So percentage is used in a MATLAB for the comment. The model parameter we took, that is A equal to 0.25 and B equal to 2 for different programs, for the dynamic system model as well as discrete system model as well. One we did using the control and simulation model using, and one we did using formula node. Then sampling time, stop time, step response as a 1, initial conditions is 0. This is for loop, and this is k equal to simple MATLAB command, k equal to 0, ts and t stop. Okay, so interval of 0.1 and we have to stop at 20. So this is the program. I just share in the chart also. So I just run it. Yes, so I'm getting the graph. So this is a second way, the same program. Even I showed different methods. The same program you can simulate in continuous, in discrete, also using the MathScript. I just share this code, the chart. So just just check whether you are able to simulate or not. Participant, please put in a chart if you are completed with this MathScript fundamentals of LabVIEW. I have also shared the code in the chart. If in student version this option is available, please try to do this. Can we proceed further, participant? If this is done, yeah, thank you, Dr. Vaibhav, thank you. So this is something about LabVIEW matchstep. If you want to save, you can save it, which will save in a .m file, which you can do afterwards. Okay, that is exit. So this is one using map script. Now I will show one more and the last experiment for the day, and then I will show some of the real-time robotics application we have done, because that setup requires a lot of complexity. I try my level best whether that will work, because I know you know that because we are doing on a virtual mode, but still I'm trying to give that simulation. So new VI will take, and the last, which is there's a one more option to simulate using math script. So this is available in the professional version of LabVIEW. Probably student version is not available. If I'm not wrong, please correct me. This master module, which is available in structure just next to the formula node. So you can use this master module directly in the LabVIEW, and you can integrate the MATLAB code with the LabVIEW. So that I will show here. So you can observe here. This is the same same type of color code what we get in a MATLAB. The green for the comment, the variables is the light blue, the functions foreign and the dark blue. So the same program I'm doing in a different combination. Now we want to simulate this discrete model using MapScript. I can understand due to limitation of student version, this MapScript is not available. Again, I would like to highlight here, MapScript module is available in structure, and just next to the formula node is a MapScript, and this version, this MapScript node is available in the professional version of the LabVIEW, not in a student version. So you have to put your MATLAB code in that MapScript module. Now we have to run this. So if we want to run this, so we have to observe the response, and you know that okay, better I will take. I just want to highlight here my participant what is the difference between chart and graph. Already I have explained very nicely. So I just take a chart as well as graph and as well as XY graph. I try to connect this MapScript node with this, but it won't connect. The reason behind this MapScript node is a combination of MapScript model and the formula node. Now, what is the combination? In formula node, we have taken the input and output. So input is already defined in my MapScript model. Now, what is my output? My output is the graph, amplitude versus time. So my amplitude is in X and time in K, because this is a discrete model. So I have to add output in this MapScript. So if you observe, see, this is the functionality of MapScript. When I do right click and add output, automatically the all variables which I have used in MapScript model or MapScript node, which is available very easily. So my outputs, one is K and one is X. Why K and X? Because we are plotting K comma X, where K is a discrete time and X is my output. But I cannot connect directly. That is the limitation of the waveform chart and waveform graph. The reason the same reason what I explained earlier, the different data types. So for that, I taught you in the morning the concept of cluster, if I'm not wrong. So cluster, where when there are combination of different data types, with the help of cluster fundamentals, you can extract the data or you can combine the data. So in morning, if I'm not wrong, we have used the unbundle the data. Now we'll use the bundle the data and get the output. What to bundle? The time, discrete time, and discrete discrete time and amplitude. Now when I connect this to XY graph, see, this is automatically showing it is cluster because there is a combination of two different data types. And when I connect to the graph, its color also change. See, and now when I will run this, I am achieving the same graph what we have set. So I just would like to highlight here, participant, there are various ways to do the control mechatronics, robotics, because all this depend upon the differential equations only. So we can use, if you are able to simulate this differential equation with different configuration, like with the MathScript node, or the formula node, or the block diagram, or using control and simulation model, or using also, you can do some of the application you can develop using PID as well. So that's all from my side. Just give me 2 minutes. I just setting up one of the last robotics simulation where I have integrated my RIO with the LabVIEW. That I just explain you or show you. Just give me 2 minutes for the integration. So actually, you can observe this is the my RIO controller. We have simple robotics application we have developed. So this my RIO, the simple motor and the caster wheel. So my screen is visible to everyone. Just show the code. So this is the project we have developed, the bot. There's a NI MyRIO. We can observe this is the series. So when you have to connect, right click and you have to connect. Now it is connected to the MyRIO. You can observe the blinking LED. And this is the code which we have written, where with respect to the keyboard application, it will go up, right, and left and down. So you can observe this is, we are doing real time. So it takes right, left, up, down, and that's all which I would like to show. And this we did it. I know it is very difficult to the virtual mode to do all the integration, but at least it was visible to my all participants. Thank you for listening me almost for 2 sessions. Thanks all. Thank you all.
Thank you, sir. That was indeed a great session. I like to thank Professor Dattatray for his great sessions on 2 topics, that is HMI design using NI LabVIEW and NI LabVIEW for CROME applications. It was very interesting to have a virtual look at the kits available at your place, sir. And thank you once again.